Okay, so I'm already in Prague since COVID, but I was in Munich before. Yeah, but it's fine. It's fine. So thanks for inviting me. So I think I'm one of the few guys who did not really actually work with Professor Grosse, but at least I remember first time when I met him because I was still a master student and I was thinking of working in like non-commutative quantum field theory or something, and there was a school for master students in Bratislava, and I remember Professor Grosse always came with his students in a very good mood because they took the boat from Vienna to Bratislava and back every day. So it was very pleasant, I guess, for you way how to reach the lectures. So I kind of secretly envied him this nice boat rides every day. Okay. So what I'm planning to talk about is the kind of integrable structure or structures that one finds in two-dimensional conformal field theory once we introduce higher spin fields, which connects to the first workshop which I visited at ESI about higher spins. So we can see near the secretary the picture of myself when I was very young and trying to learn these things. But before getting there, I have like 2 slides of summary, what you can kind of take home if you get lost on the way. So the main point is that if the two-dimensional conformal field theory has like large families of commuting conserved quantities, and if you want to diagonalize it, there are Bethe ansatz equations of this form. There are actually different types of Bethe ansatz equations that one can write for 2D CFT, but this second one is the one that I find very nice and symmetric. And if you compare that to the all these Bethe ansatz equations that were written by Bethe, probably not in this form, 80 years before, you see that they are almost identical. The only difference, the only real difference between the two sets of equations is this factor here versus the factor there. So the interactions between pairs of Bethe roots, instead of being governed by rational function with single pole and single zero, here they are governed by a rational function which has 3 zeros and 3 poles. And that's the only difference. So it's rather surprising that it took people like 80 years to realize that such a small modifications of the original Bethe equations of Bethe really describes this rather complicated integrable structure of 2D CFT. Okay? And then there are other Bethe ansatz equations that one can also write down for 2D CFT, I mean, for Virasoro algebra. And again, this can be compared to much older Bethe ansatz equations. So those on the first line are well-known equations which maybe people wouldn't even call Bethe ansatz, but they are equations that are satisfied by zeros of the Hermite polynomials. So if you study just simple quantum mechanical harmonic oscillator problem and you look at definite energy eigenstate, the places, the points on the real axis where there is zero probability of finding the electron, they satisfy system of equations like that. And actually, and it's used in matrix models and so on. What is less known that actually same the positions of zeros of Hermite polynomials also satisfy this second set of equations with L equal to 0. But if you allow these second equations also, they have many more equations labeled by Young diagrams, and those solutions of these equations describe kind of eigenstates of the Hamiltonians that you can construct in 2D free boson. Okay, so harmonic oscillator is kind of free quantum mechanical problem, and the quantum field theory problem, that is the analogous free problem, is described by very similar equations. And finally, if you consider Virasoro algebra, the equations written by Bazhanov-Lukyanov-Zamolodchikov can be in the correct with correct choice of coordinates again described in the same way as those for free boson, but this external potential or force instead of being coming from quadratic potential is now coming from the nth degree potential. But the rest is the same, so there is some kind of, let's say, centrifugal force or some kind of interaction with particles start at origin, and then there is this Calogero-like interaction that is kind of the main important thing that is really controlling many of these equations. And by the way, I'm convinced that the fact that here there is this third power is really related to the fact that this function is third degree. I think that's not accident. I think that's really, again, the change that you have to do to get this richness of solutions of these Bethe ansatz equations. Okay, so this is kind of where I would like to get. But before going there, the natural context for these kind of integrable structures are extensions of Virasoro algebra by higher spin fields, and these go under the name of W algebras. And they appear at really many places because their definition is very natural one, and there is very little input that goes into definition of W algebra, but then you get a lot as like very rich structure as output. So because of this, you can really choose whatever area you like, and you will probably find some W algebras showing up there, especially in four-dimensional quantum field theories with more supersymmetries. There are different constructions how you can get kind of W algebra, typically controlling some subsector, a protected or BPS subsector of the theory. But also, you know, in ADS-CFT, ADS3 CFT2 correspondence, if you consider higher spin gravity, then the holographic dual is governed by these algebras and so on. Okay, so this is just like trying to convince you that they are interesting and useful. So the simplest W algebra, apart from trivial W algebras like the Virasoro algebras, Virasoro algebra is the algebra W3, and this algebra was, maybe I can use this. This W3 algebra was found by Zamolodchikov already 1 year after the famous paper of Bazhanov-Lukyanov-Zamolodchikov. So that again illustrates that the definition is a very natural one, and it's really, as soon as you have Virasoro algebra, you can ask yourself, you know, what are other algebraic structures of the similar type. So what he considered was this Virasoro algebra written in the form of operator product expansions, like in conformal field theory, and then he tried to extend it by additional field of dimension 3. And he chose this field to be a spin 3 primary, so that immediately tells us what is the operator product expansion between the stress energy tensor and W. But in order to close the algebra, he also needed to write the OPE of W with itself, okay? And there are certain requirements, like some scaling and so on, and then you also need to satisfy analog of associativity conditions. And he imposed that by requiring the crossing symmetry of 4-point function with these insertions. And he found a unique answer, which, you know, it looks rather complicated. That's a little bit similar to Olaf's talk yesterday, that you really start with something natural, but you get some kind of explosion of things. But they are like uniquely, what is important is that everything here, every single number here is like uniquely determined, and it even has meaning. So for example, the reason why this factor 5c plus 22 appears, it's just indicating that when the central charge is minus 22 over 5, something interesting is happening, and we know that it's exactly the central charge of the Young model, which is like kind of the simplest minimum model of the Virasoro algebra. So everything here has like meaning, okay? But the main point is that one of the fields that is appearing on the right-hand side, there is not just T and W. Sorry, W doesn't appear because of the Z2 symmetry, but there is not just T, but there is also a composite field lambda, which is basically T square. Okay, so the algebra is forced somehow, imposes on you the nonlinearity. You cannot really choose to eliminate the nonlinearity. But this is something really to be expected, because if the dimension of these fields is 3, as we assumed from the beginning, then the highest singular part is of degree 6, and then the smallest one has degree 1 multiplied by a field of dimension 5. So you see that since stress energy tensor square has dimension 4, there is space in the singular part of the OPE for these nonlinearities. Okay, so the reason why we don't see it when we study like affine algebras or Virasoro algebras is that it's just, you know, counting the dimension, we see that there is no space in the singular part of the OPE for these nonlinear terms. But as soon as you have at least one field of dimension 3, they show up and they are really important. Okay, so this is one thing that people, like, we should not be scared of the nonlinearities. They really need to be there. Okay, and then after this, people studied other examples of W algebra. So you can basically choose any spin content, so any collection of dimensions of your generating fields, and write the most general ansatz for the operator product expansion, and impose the associativity conditions and see how many algebras you find. Okay, so there is one very interesting family of algebras called Wn, and those are somehow associated to SLN family of complex simple Lie algebras. So this is this kind of arrow. So there are various constructions where starting from SL2, you can produce Virasoro algebra. And if you run these constructions starting from SLN, then what you end up with is the algebras Wn. Okay, so this again shows how natural they are. Then around 10 years ago, in the context of ADS3 CFT2, Gabriel and Gopakumar were studying what happens, because they were kind of forced to look at this, what happens if we just, okay, sorry, I forgot to mention that the generating fields of the algebra Wn have dimensions 2, 3, up to n, okay? And then Gabriel and Gopakumar just asked themselves, what happens if we don't make this n to be the upper bound on spins, and what if we instead consider algebra generated by a single field in every dimension greater than or equal to 2, okay? So they just kind of relaxed this condition that the number of generating fields is finite and that it terminates at n, okay? And surprisingly, they found two, or maybe not surprisingly, they found two parametric family of algebras, which is actually not surprising because already here we had two parameters. We had this rank-like parameter n, and then we had the central charge, which was always there, okay? Just like in Virasoro algebra, we have the freedom to choose central charge, whatever we like. So they found two parametric family. And the origin of these parameters is, as I said, the central charge and this rank-like parameter. And somehow this algebra W infinity interpolates between all W and algebras. So I should say that unlike SLN, these algebras don't sit as subalgebras of each other. So W3 is not a subalgebra of W4 and so on. But it turns out that this W infinity contains all these algebras. So more properly saying, there is this second parameter lambda, and if we choose this lambda to be a positive integer, then there is a very big ideal appearing in this W infinity, which basically is generated by all spins higher than n, and we can consistently put this to 0, and then we reduce this Wn. For people who are familiar with these higher spin algebras, there is similar construction where this SLN family can be interpolated with continuous value of this complex value of this rank parameter n. So it's very analogous construction. And finally, for some things that I want to tell you in this talk, it's also convenient to add additional spin 1 field, but this field can be decoupled. So it's just kind of convenient field, like free boson, that is useful for bookkeeping, but it does not really interact with the rest of the algebra at the level of operator product expansions. And again, the analogy of this spin 1 field is when we consider GLN instead of SLN. So you know that the diagonal matrices again commute with the rest, and for some things it's convenient to consider GLN, for other things it's convenient to stay with SLN, okay? Now probably the biggest surprise that Gabriel and Gopakumar found, at least for me, is the triality symmetry, which is some kind of symmetry which tells you that actually for every value, fixed value of the central charge, there are 3 values of these rank-like parameters which give you the identical algebra. Okay, so the structure constants, if you look at the operator product expansions, they kind of depend in cubic way on this rank-like parameter. So for every choice of C and lambda, I can find other 2 values of lambda which give me the same algebra. So they coined this symmetry permuting the lambda parameters triality symmetry. And it shows up at many places in the representation theory, as I can show you on the next slides. But just one thing. So these three rank-like parameters are related by this type of condition. So I have, instead of parameterizing the algebra by central charge and one lambda, I can parameterize it by three lambdas, modulo this relation, and then the central charge is given by this simple symmetric form. Okay, so this is like convenient parameterization of some things. So now one can ask whether or not this triality symmetry is real. So there are different like quantities that you can calculate in the algebra, which really manifest this symmetry. So for example, here in this picture, you see manifestly that there is this rotation symmetry by 120 degrees, plus there is also Z2 symmetry, which is like the complex conjugation, or the duality symmetry in GLN. So what this picture is values of parameters of the algebra. Like this is like lambda plane, let's say, and the curves are positions or locus in this lambda plane where the vacuum module of the algebra has some null states. Okay, so just for people who know conformal field theory, you know that if you tune central charge to some special rational values, then there are not all states that you generate from the highest weight state by applying the Virasoro generators are independent. So there are some equations of motions or null states, and when this happens, this happens for like well-known list of central charges. If you look at the same question in W infinity, you find that there are these like infinitely many curves in the two-dimensional lambda space. But the reason for showing you this picture is that really this symmetry is real and controls the representation theory. Another place where you can see this symmetry is if you look at the character of the vacuum representation, which is basically counting all the local fields that the algebra has. So it's quite easy to convince yourself, if you know a little bit of Virasoro representation theory, that this vacuum character is given up to overall factor by such a function with this expansion. So you see, for example, that I have one field of dimension 1, which was my spin 1 generator. Then I have three fields of dimension 2. So there is this Virasoro stress energy tensor. Then there is a square of spin 1 field and derivative of spin 1 field. Okay, so we can do this simple counting. And you see that this is the function that counts all the states. And maybe surprisingly, this function is known, again, from 19th century math. So it's the famous McMahon function, which is counting 3D Young diagrams. So it's counting configurations of boxes in the corner of the room, okay? So the number of local fields is of dimension n is given by number of configuration of boxes, of n boxes that you can put in the corner of the room. Here you see also very naturally how the triality symmetry permuting the three parameters can act. It simply permutes the coordinate axis, okay? So it has a very nice combinatorial realization. Also, these truncations Wn that I told you when lambda is an integer, again, that has a very nice combinatorial meaning. It just tells you that you should restrict the growth of your 3D Young diagrams to have at most n layers in one of the directions. So things can grow, but they are constrained in one of the directions, and so on. So typically, most of the representation theory questions can be answered in terms of combinatorics of these 3D Young diagrams. And you don't need to study the vacuum representation. You can study also other primaries and so on, and they just correspond to turning on some non-trivial asymptotics along along the coordinate axis and so on. Finally, this is just one strange picture, but I wanted to say even the things that you are very familiar with, or at least some of you, like the minimum models of in 2D CFT, like the Ising model or Liang or Potts or whatever, those minimum models, their characters have also quite simple combinatorial interpretation, but in that case you have to consider kind of periodic configurations of boxes. So instead of having like one corner, you have kind of a whole tiling of the plane where there are infinitely many corners. So you can like wind it on cylinder or whatever. So if you start adding boxes to some initial periodic configuration like this one or like this one, and count in how many ways you can add boxes, you will reproduce the characters of the minimum model primaries, which are usually written in terms of theta functions or some more complicated things. Okay, so they really have very nice and simple combinatorial description. Finally, I had one slide that is comparable to what we saw yesterday, that if you just approach things directly, things can get very quickly out of control. So there is like this exponential growth of number of fields, and their operator product expansions are very complicated. So this is just like very small part of the OPE of spin 3 and spin 5 field. And even in good bases where you eliminate most of the nonlinearities. So the algebra itself is really very complicated if you kind of approach it in too straightforward way. I mean, you have to be much more clever than, what I would be, for example. So, and this is motivates for the next section. So there is a completely different description of the algebra, which is given in terms of like as associative algebra with generators and relations. And I will have later a picture how these two descriptions are related, but they look nothing alike. They are like completely different. And if someone just gives you this list of relations, it's really hard to believe that it should be equivalent to infinitely many relations of this type. Okay, but this description is very efficient for the representation theory. So we have three sets of generators, psi, E, and F, and the description is kind of 3D version of harmonic oscillator or something like, but not really 3D harmonic oscillator of quantum mechanics, but some kind of extensions of the usual harmonic oscillator. So these psi j's, they all commute with each other. So they give you infinite collection of commuting quantities, which you can try to diagonalize to describe the eigenvectors. So that gives you nice Cartan-like subalgebra. And then we have ladder operators like addition, creation, and annihilation operators. And together they satisfy these relations. That's not all of it. Also these and these. Okay, so as it is, it looks very complicated. But again, I will write it in a slightly simpler way. What is important at this point is that there are, again, like 3 parameters, modulo 1 relation. So exactly the same counting as before. And there is also manifest permutation symmetry between these 3 parameters, just like before. So the way we see the symmetry is kind of tautological, because the whole algebra, I can show you the previous slide, depends only on these symmetric combinations of the parameters. You see, these sigmas are the only kind of numerical parameters that enter this. And you should not think of this as being like Lie algebra or Lie superalgebra, because there are both commutators and anti-commutators involved, but there is no grading that would tell you whether there is a commutator or anti-commutator. Okay? It's just associative algebra given by generators and relations. You can simplify this by introducing generating functions for these 3 sets of generators. Sometimes people call it Drinfeld currents. And then the main part of the algebra, so all these 4 long relations, they can be written as exchange relations. So if I have this Drinfeld current EU, EV, and if I exchange it, then they agree almost up to, they are equal up to multiplication of this structure function phi. And phi is just a rational function which has 3 zeros and 3 poles, and that's the function that was appearing on the first slide in this Bethe ansatz equations. So this is like the unique structure function that controls this whole algebra in this Yangian description. And actually, this structure function is very closely related to this picture of 3-dimensional Yang diagrams. So the positions of zeros and poles, you can kind of imagine it as being associated to positions of the vertices of the basic cube that is kind of controlling the representation theory. As I said, the representation theory in this description is much simpler. So we can find bases of the representation spaces which are labeled by objects like this. So this whole picture is like a label of the eigenstate of all these size, and the associated eigenvalue, which is this, can be completely written in terms of this structure function phi, and the coordinates of all these boxes that appear in the label of the states. Okay, so the whole kind of representation theory reduces to combinatorics of these 3D Young diagrams. And even the creation and annihilation operators, they are kind of controlled by the same structure function phi. So I didn't write it in detail, but schematically, this is how it looks like. And yeah, maybe I didn't emphasize this. E's and F's, the creation and annihilation operators, they add and remove boxes. Okay, so that's kind of what this algebra does, and these psi's act diagonally on these configurations. So now I have one slide which tries to kind of illustrate what this, how these two pictures are related. So the full algebra, at least if you like simplify these parameters, can be thought of having generators labeled by spin and Fourier mode. So this spin runs from 1 to infinity, as I said at the beginning, while the Fourier mode runs from minus infinity to infinity. So that's the usual Fourier mode along cylinder or circle. And then the usual CFT description in terms of operator product expansions introduces generating functions in this horizontal direction. So we sum over all Fourier modes, and that's how we get our local fields in CFT. On the other hand, what this Yangian description does is that it resums over all spins at the fixed Fourier mode. Okay, so I have this creation, annihilation, and Cartan generators where I kind of fix the Fourier mode to be -1, 0, and 1, and sum over all spins. Okay, so each description kind of focuses on like different aspect of the algebra. But so far, I don't know any like satisfactory kind of description which would like resum all of it. So you can kind of zoom on one thing or the other one, but to combine it, it's a little bit more complicated. There is actually shuffle algebra description of the half of the algebra. So all the creation operators can be described in terms of what people call shuffle algebra, and that has some analogy with the model product. I mean, it's not really the same thing, but it has some resemblance of that. So maybe there are even some connections with non-commutative geometry. But yeah, so far this is the thing that is most explored. Any questions? How much time do I have? 28 minutes. Since I started, yeah. So like 15 minutes after. Yeah, I think yes. I think it has. I can show you the formula after the talk. Basically, there the basis, the generators of algebra, you choose to be all symmetric polynomials, but in every finite number of variables. So you have part of algebra with symmetric polynomials in one variable, then in two variables, three variables, and so on. And then the way you multiply it, you kind of take these two symmetric polynomials, let's say in 3 and 4 variables, and then you multiply by that structure constant. Then you symmetrize, which this symmetrization kind of is doing these shuffles because they are already symmetric partially. So you kind of really shuffle them as the deck of cards. So I think it is connected. But this shuffling involves also this cubic structure function. So that's kind of the characteristic thing of the whole theory. It's, yeah, people like Fagin, you know, this Russian school, and also Japanese, they have many, they know a lot about these shuffle things, but it's just, okay, anyway. Yeah, so now I wanted to say a bit about these integrable structures. So what I mean by this is just choice of some infinite collections of commuting quantities and then trying to diagonalize those. Okay, and we already saw one collection of these quantities which are just this size. So in this Yangian description, I have just directly from the definition of the algebra, I have infinite collection of quantities, and I told you that they can be diagonalized quite simply, and their eigenvectors are labeled by configurations like this, and even the spectrum is known. So in this picture, everything is simple and clear. The problem is that these are not the kind of Hamiltonians or commuting quantities that you would pick from the conformal field theory point of view. So from the 2D conformal field theory point of view, you would like your Hamiltonians to be like zero modes of some local currents. And these Yangian quantities are non-local. Like maybe later I will have time to show you the formula, how non-local they are. So there is, since beginning, again, since paper of Bazhanov-Lukyanov-Zamolodchikov in '94, but also in the papers about the KDV, as we heard about, there are very long known kind of local Hamiltonians that people study. So they exist also in this quantum setting, and they are natural for many things. So the question is how to diagonalize those. And it is quite complicated or indirect how to diagonalize them. And there is some kind of description of their simultaneous eigen vectors and eigenvalues in terms of what people call operas or like differential operators, which I will show you later. But yeah, and then the connection between these two choices of commuting sets of Hamiltonians is also not completely clear. So they are different. It seems as if the whole algebra had inequivalent choices of Cartan subalgebras in some sense. So, but before going there, there is a very simple geometric picture for the classical limit of this integrable structure. So now I'm talking about this second integrable structure, so these local quantities. So the classical limit or classical version of this whole thing that I'm talking about is the KdV or Kp hierarchy of integral partial differential equations. So the classical limit of Virasoro is this KdV, and classical limit of the W infinity is the Kp. So let's, for simplicity, focus on Virasoro algebra. So the classical analog of the stress energy tensor is the Schrödinger potential. So I consider one-dimensional Schrödinger equation with some arbitrary potential. And this potential is the classical limit of the stress energy tensor. And then the problem that people ask is if there are any deformations of the potential which don't change the spectrum of the Schrödinger operator. So if there are isospectral deformations. And it turns out, I mean, you can easily guess that definitely there are some. For example, the rigid translation of the potential doesn't change the spectrum. Okay, so definitely I can do something with the potential without changing the spectrum. But perhaps surprisingly, there are infinitely many deformations which one can do, which really change the shape of the potential. So the picture that you can have in mind is that you can take the potential, for example, on the infinite real line, which is given by two threshold Taylor potentials, which are separated far from each other. And then you can let this potential evolve according to KdV equation. So these two kinks, they kind of start approaching each other, and as they get closer, they deform. So in the middle, there is some like, non-trivial profile and so on, and they keep on going until they are again separated and become again. Exactly. So there are infinitely many families of these deformations, and the simplest one, which is not the trivial rigid translation, is exactly this KdV equation. Okay, so and this is part of, again, what was discovered, I guess, in 70s or 80s, which goes under the name of quantum inverse scattering or classical inverse scattering. Anyway, it's the way of solving the classical KdV equation by first of all translating it to this quantum mechanical problem, then evolving it on this side, which is very simple, and then, I mean, at the level of spectrum, and then again reconstructing back the potential from the evolved spectrum. Okay, so people who study classical integrability of these equations, they kind of know this very well. But what is important, that all these, so there are infinitely many continuous deformations of this potential, and they can be organized into a Hamiltonian system. So I can consider infinite dimensional space of all Schrödinger potentials, modulo, the boundary conditions, but that I don't care about because all this discussion is kind of local, and algebraic mostly. So it works for different choices of boundary conditions. I can study it on circle, or I can study it on the real line with like fast enough decay and so on. Okay, that doesn't really affect this integral structure. So I have this infinite dimensional space of potentials, and I can equip it with Poisson bracket, which is like this. Okay, it might look so the both kind of coordinate and momentum, they are contained in this string potential U of x, and the bracket is like this. It may look complicated, but actually it is just a kind of Fourier transform of the Virasoro algebra. Sorry. Short derivative. I think that appears slightly differently. Short derivative appears, maybe it's connected, but the short derivative appears here if you do kind of holomorphic, analytic change of this coordinate. This potential transforms with short derivative, just like stress energy tensor. So that's kind of classical way how you see the short derivative even in this classical setup. Here, I would say that this thing on the right hand side, maybe because it has the third derivative, maybe it can be related to short. Yeah, but anyway, it is the Fourier transform. I mean, the Fourier transform of this is the classical Virasoro algebra. Okay, so if you here the central charge doesn't somehow matter. Classically, you can rescale the central charge to anything that you like. Yeah, but I mean the central charge you can kind of in the classical limit you can rescale it to anything that you like. Yeah, it's on zero, but its value doesn't like matter. Okay. In the quantum setting, the central charge really has scale, so there the different values matter. But here you can kind of replace it. But no, I consider all of them. All of them. I have this bracket, but now what I want to say is that there are this kind of infinite collection of Hamiltonians, which if you follow these flows, you don't change the spectrum. Okay, so the potentials with the fixed spectrum, they are connected by these infinitely many flows. So there is some kind of foliation or something of that infinite dimensional space, and the slices are kind of spanned by this isospectral deformation, by these flows. Okay. So that's the rough picture. And so this is the classical limit of the Virasoro algebra, and so the main point is that it has structure of classical integrable system. And now, of course, you can ask what happens if you quantize it. For example, do these Hamiltonians, do they exist? Does there exist like quantum deformation of these? Okay? And the answer is yes. So these are the local quantities that were considered by already, I think in 70s, I forgot the names, but they were mainly, I mean, the first important paper where they were really studied in detail are those of Bazhanov-Lukyanov-Zamolodchikov. So you can just take stress energy tensor, and it's zero Fourier mode. So that's the L0 of the Virasoro algebra up to a constant. Then you can take, let's say, zero mode of the T square. That's the analog of this zero mode of the U square. Okay. And then again, by construction, it commutes with L0 because you are taking zero modes. Okay, so this is not really interesting. This is always there and always commutes with L0. But the surprising thing is that there are infinitely many other, again, integrals of local fields, like this and others, which all commute among themselves. Okay, so definitely this integral structure survives the quantization. Okay, and then you can ask, what is their spectrum, how to diagonalize these. So since L0 is part of this family of commuting quantities, it reduces to just diagonalization of finite matrices. So you pick your central charge, you choose your primary, and then you get level by level, you get just bigger and bigger matrices. And you can just try to see if there is any way to diagonalize, hopefully all of them. And BLZ, they found a way how to describe the spectrum in the context of ODE-IM correspondence that was initiated by Dori and Patel. Yes, so this is just example. So for example, for this Liang model, which as I told you is like the simplest CFT, at level 5, I have matrices like this. Okay, so they are very concrete matrices. And the question is just like how to diagonalize them, in kind of all at once or something. So maybe the only thing that I can say in the remaining 5 minutes is this answer by VLZ. So what these people studied, inspired by this ODIM correspondence, so they studied differential operators of this type. You see that there is again another instance of Schrödinger-like operator, but in people who know more than me about this, they kind of emphasize that you should not try to identify this Schrödinger operator with the one that I showed you in the classical limit. So apparently they should not be thought of as being related in any way, but I think, yeah, I don't always, I still sometimes hope that there will be some connection. Okay, so you have just concrete second order differential operator with some rational potential in the complex plane. So this object is identified with the highest weight state, with the primary in the 2D CFT. And then if you want to describe descendants, so the states that are at some Virasoro level, you are instructed to add additional. So this has singularity, let's say, at 0 and at infinity, and nowhere else. And if you want to add descendants, if you want to dress this differential operator to describe descendants, you are instructed to add additional singularities somewhere in the complex plane with at most quadratic poles, so that the points where you insert them remain the regular singular points. And furthermore, I mean, these positions and also this is a priori not fixed, but then you require that there is a trivial monodromy of the solutions of this Schrödinger equation locally around those points. So basically, if you take your Frobenius solutions around those singularities, you require that there are no logarithmic terms in those two solutions. So this is a non-generic property. Generically, you would have logarithmic behavior of one of the solutions because this thing is chosen in such a way that there is this resonance. So the indices in this Schrödinger equation they differ by integers. So because of that, there are these logarithmic terms. But if you require that these logarithmic terms don't appear, that gives you exactly as many equations as you need in order to completely quantize or fix these positions of these singular points. So there is only like finite number of solutions of this problem, and these solutions again are by the work of ODIM people or BLZ are in one-to-one correspondence with these descendants at given level. Okay, so this is kind of maybe more geometric description of the quantum states in the algebra. And you see that, by the way, these equations that quantize these positions of these are exactly these Bethe equations that I talked about. So these positions of center, sorry, x should be z, I should correct it, they are the same. So you see that they kind of interact via this inverse square potential. So this is Calogero-like interaction between the positions of the centers. This is some kind of coming from here that controls the primary, and then n is related to the central charge. Okay, so this is an example of the Bethe equations that appear here. And once you find solutions of Bethe equations, you can then find the eigenvalues of all these commuting Hamiltonians. For example, the first non-trivial one, this I3, which was quadratic in the Virasoro generators. So this one is given by just like some symmetric polynomial in the positions of the center. So I wrote it completely, but these terms are just some overall contribution from the primary, but this is really the dependence on the descendant, and you just see that it kind of is controlled by the center of mass of these positions of centers. Yeah, it's not clear how to do this for higher ranks concretely, so there are some general proposals, but to really check it at the level of equations and have really numerical values of everything that is not known. And it's also not known at this point how is it related to these Yangian quantities. I mean, at this point of my presentation. Now I would have, but I think I should finish now. Now I had a few slides. For those who would be interested, you can read the papers or ask me afterwards. There is a way how to connect these two families of the integrable quantities by studying what people call instanton R matrix. So there is a kind of interpolating family of Hamiltonians, which for one value of parameter gives you the local quantities. For the other parameter, it gives you the Yangian quantities. Okay, so this I have to skip, but there is a very nice connection to spin chains and all these things. Yeah, but sorry. No, this I didn't even want to show. So Now the final, yes, this is unfortunately the old version. So I tried to find picture with 80 candles, but there are just 40, I think, in this picture. So I think really the cake would have to be much bigger. And it reminded me, it's a pity that I don't have the newest version. This really reminds me of the picture that people have of the old Bologna, the medieval Bologna, which had like hundreds of towers instead of the current two or how many. So it's really like crazy if you see these old pictures, like how people imagine. So this is, I think, how what we will celebrate soon. Okay, thanks.